Okay, so at the end of the last video, we were talking about relative velocity and how if you're in a river or in an airplane in the air and you might aim some way, but a current or a wind current or a water current can carry you in a different direction. So your resulting velocity will not necessarily look like what you had set out to do. What you had set out to do will be one component of your overall velocity. And the other component that has to get added in is the wind or the air current. And so this one at an angle is the resultant. Of course, once you realize that, then you can make allowances for it. So as the video ended there, I was talking about, imagine that you are in a real river, not like, a big river, and in a canoe, and you have a whole ton of supplies, and you're starting here, and the campsite is over here. And you want to end up directly across, because even though the river's flowing this way, you don't want to end up down here somewhere, because if you do, then you're going to have to pick up your canoe and your sleeping bag and your food and your cooler and all your gear and trudge down through the overgrown brush where there's crocodiles and alligators and monkeys and elephants and who knows what else to get to the campsite. That just seems like a lot of work. So instead, you're like, I've taken a physics course. I know what to do. If this is east, and this is west, and this is north, and this is south, and we know the river is flowing south, so that if you aim for here, you'll end up down here, then instead, you aim further north. And you allow the river, looking for another color, you then allow the river to do what it's going to do anyway, but this time you've made allowances for it, and so when you get to the other side, you're at the spot you want to be. Okay, and that's what the second example on the back side of your sheet says. So the same person wants to end up directly across the river and not some distance downstream. The velocity of the canoe with respect to the water and the water with respect to the shore are the same. So the water with respect to the shore, this velocity was 2 meters per second south. Which one is it that the canoe's doing with respect to the water? This one. This one is 4 meters per second. But it's no longer east, right? It's at an angle. So the question says, what angle does the canoe need to travel so the person will end up exactly across? So you're looking for this angle. You can find it. It's a right angle triangle. You have the opposite side and you have the hypotenuse. So you can just use sine theta is equal to 2 meters per second over 4 meters per second. That's 0.5. So inverse sine of 0.5 should be 30 degrees. Which way are we measuring off of? East, 30 degrees. Which way do you have to head? North. So for part A, the answer is east 30 degrees north. Now the one thing I had said to you the other day when we were doing the drawing to scale stuff, I had said we couldn't put meters per second on our diagrams unless all the times were the same. But the times are the same here, right? The time it takes you to cross the river is the same as the time it takes the river to carry you down. So the times are the same here, so it's okay that we're using in these diagrams all meters per second. Notice I didn't put the 800 meters in here. You can't mix units, so we only brought the 800 meters in after when we use the VAV, but not in the diagram. All right, so we found our angle. Part B says, what will be the magnitude of the canoe's velocity with respect to the shore? Well, this is the one now that it's doing with respect to the shore. So it wants to know, what will this be? Well, it's Pythagorean theorem again, except this time you're finding one of the sides. So it's going to be 4 meters per second squared equals v squared plus the 2 meters per second squared. Right? So v squared will equal 16 meters squared per second squared minus 4. So the square root of 12. So your speed with respect to the shore should be 3.464 meters per second. Notice, and that's going east. Notice it is significantly less than what it was over here. Because over here, you were going 4 meters per second straight across, and then the current was pushing you down. Here, you're actually going into the current, right? You're working more against the current, and so your overall speed is going to be less. Okay, so there has to be some drawbacks, like you're being smart and aiming into the current to let the current get you to the spot you want to be. But in doing that, you're going to lose some of your speed. Okay, and now the question wants to know, how long did the trip take? Remember, in the previous example, it told us the distance across here was 800 meters. Remember, I said that when you use this 800 meters, you have to use the velocity that's going in the same direction as it. So this time we have to use our 3.464 meters per second. So we know that VAV is equal to delta D over delta T. So delta T will equal, rearranging, delta D over VAV. So 800 meters over our 3.464 meters per second. This time, the time it takes us to go across is 230.94 seconds. So it actually takes us longer than it did in this example. In this example, it took us 200 seconds, okay? But then we ended up too far downstream and we'd have to go back. In this question, it takes us 30 seconds longer, but we're where we want to go. We don't have to then carry our stuff anywhere else. Okay, so it's really about adding the different velocities together to get the resultant velocity. Okay, and the resultant velocity, when we're talking about like what the water current is doing or the wind current is doing, another way of saying it is, what would a person on the shore see you do? Like, you think you're aiming straight across, but the person on the shore sees the overall effect of your velocity plus what the river's doing to you. Okay, so now if I've completely confused you, I'll try to fix it when you come back to class. But try on page 110, and you kind of have the numbers here, 21, 22, 24, 25, and 27 on page 110. You do not have to draw these to scale. These will all be right-angled triangles, so you can use the Pythagorean theorem here. Okay, so give them a try. We'll go over them the next day I see you. Promise.